We'll start this lesson where we left off from last class, which is one of these tougher horizontal and vertical tangent problems. So I'm asking you to find the locations of horizontal and vertical tangents to the following. This is a graph of a rotated ellipse. Just like last class and just like on your quiz, you need to find the derivative. You need to then set it equal to 0 and see when it's undefined. So you set the numerator equal to 0 and you set the denominator equal to 0. I'm going to do the horizontal tangent part. We're all going to do the derivative part. So everybody take the derivative of this guy. dx everything. Make sure you realize that the xy in the middle is a product. It's a common mistake made. F prime g plus g prime f plus derivative of y squared, 2y dy dx equals 0. Subtract 2x, subtract y. Factor out the dy dx. X plus 2y is equal to negative 2x minus y, or dy dx equals negative 2x minus y over x plus 2y. Well, let's find our horizontal tangents. What do I do, Mr. Glupke, to find the horizontal tangents of that original equation?
Set the numerator equal to 0.
Set the numerator equal to 0? Perfect. Well, what do I do now? Mr. Rinderknecht? Exactly. Solve for one of the variables, because we don't have a situation with just one variable like you did on your quiz, where you can just solve for a variable and then find your others by plugging it back in. We have to solve for a variable, and now we have a system of equations that we can use. We know that the y's are the opposite of the double of my x's, and these y's and x's have to work in this original equation. So we'll take this y is equal to negative 2x, and we'll plug it back in to our y's. Now, you guys should have done that on your quiz today, only what you should have done is you would have gotten y is equal to like 1 or something, plug 1 back into the original equation to find your x's. There was multiple x's for your y. And just like when you found your y or your x, there was multiple y's. And you guys should have found 4 points total. Okay, some of you are like, oh, but that's okay. You won't make that mistake again, hopefully. So we get x squared plus x times negative 2x plus negative 2x squared is equal to 27. That's x squared plus negative 2x squared plus positive 4x squared is equal to 27. We get 3x squared is equal to 27. We get x squared is equal to 9. We get x is equal to not just 3, but plus or minus 3. Well, that's just half of my point. I can get the other half where? Yes, the negative 2x equals the y is actually going to be the easier equation to use, we would get the same values no matter which equation we use if we plugged in 3 in for y up here, or if we plugged in -3 in for y up here. But we know this relationship has to hold, so I plug in 3 for x, I get -6 for y. I plug in -3 for x, I get +6 for y. These are the locations of my horizontal tangents. Well, your turn. Figure out your locations of your vertical tangents. Now, for this one, I wouldn't have solved for y. It's actually just okay if you solve for the other variable x. You did solve for y, it's going to be fine. You'll get the same thing as I did. But when I solve for x, I just go back into my original equation, substitute y, and what we'll find out shortly is that since kind of we have x squared, xy, y squared, when I plug in -2y, I'm going to end up with like the same answers as I did for my x's. Get 4y squared plus -2y squared plus y squared. Well, this looks familiar. I end up all the way down with 3y squared is equal to 27. That's 29. I think I had sometimes. Divide by 3, you get y squared is equal to 9. Or you get y is equal to ±3. Well, let's not be too afraid. Neither of these points have y's that are ±3. Okay, so we have just 2 new points. One with a y of +3, one with a y of -3. I plug in +3 into this second equation. That's really going to help us. I get -6. Plug in -3 into the second equation. I get +6. And here I go. Well, let's double check to see that's correct. Let's graph x squared plus xy plus y squared equals 27. I'm looking for horizontal tangents at 3, -6, 3, -6. Tangent there looks to be horizontal. I'm also looking at -3, 6, -3, 6. Got it. Vertical tangents. -6, 3, -6, 3. That's a vertical tangent. And 6, -3. 6, -3. Boom. We win. Okay? It's fun when you can see it visually and you're not just like, I guess this is right. You know, you can actually graph and you're like, yeah, boom, I got it. All right, so be prepared for a question like that for your next quiz. Finding second derivatives of implicit equations. Let's go steps involved in this. Typically, you'll ask to find d squared y, and this is just that notation. We'll show you again where it comes from, over dx squared in terms of x and y. That will be the question that's asked of you. Find d squared y over dx squared in terms of x and y. They make sure they include this in terms of x and y for a very good reason. Okay? Well, how do I find a second derivative, Mr. Gordon?
You take the derivative of the first derivative.
That's exactly right. Same thing here with implicit equations. I just take the derivative of the derivative. Well, let's go do that. Let's start by finding my first derivative of this circle. 2x plus 2y dy dx equals 0. Subtract the 2x, divide by the 2y. You get negative 2x over 2y, or negative x over y. Well, we need to take the derivative of this derivative. Let me show you where the d squared y over the dx squared comes from. So what we would do is take the derivative with respect to x again. Then the derivative of dy, you kind of do that multiplication guy. Okay? You don't do it always. I don't want you to always think about this, but it's the reason why. You got d and then dy giving you the d squared y. It's the second derivative. And then on the bottom you got dx, kind of like times dx. Well, that's where the dx squared comes from. You should write it like this, because it should be like d squared x squared, but typically books write it just like this. Okay? So we found dy dx implicitly. We are going to take the derivative again. We get quotient f prime g minus g prime, the derivative of y, is dy dx times negative x all over y squared. Okay, that's an answer. That's fine. But it's not the answer I'm looking for. Right? I'm looking for d squared y over dx squared, which is what I have, but in terms of x and y. I have x, I have y, and I have dy dx. This is like an extra thing that I don't want in my second derivative. I'm not asked for. So what do you think we need to do, Mr. Kaiser?
Replace it with the equation of what dy.
Exactly. We know what dy dx is. It's negative x over y. So step 3 is to substitute for dy dx. So I'm going to move that up here. It's going to be d squared y over dx squared equals negative y minus negative x over y times negative x over y squared. And I got it. And that's an answer. That's a great answer. However, what do you think I can do? Simplify. So this is good. This is an answer. However, let's go down the rabbit hole. I'm going to multiply my x's. We get y minus x squared over y squared. Yeah, that's nice, but I don't like having fractions inside of fractions. So let's give this guy a common denominator. Let's multiply by y over y. So let's go d squared y over dx squared. I'll get negative y squared minus x squared over y squared. Yeah, well, I don't like that either. Maybe I'll just multiply by 1 over y squared. Maybe I'll just make this bottom y cubed. All right, that's nicer. But I can go a little further. Why don't we factor out a negative 1 up here? Well, that's cool. Actually, whoa, that's awesome. Look what I can do. What? Where did the negative 25 come from? Oh, look at that. I know what x squared plus y squared has to equal. It has to equal 25. Well, this is your simplified second derivative. Now, what's fascinating about this? So let's think about my circle with a radius of 5. X squared plus y squared is equal to 25. Let's think about when my y's are positive. I'm in the top half of my circle. Okay, so y is 1, top half of the circle. If I plug in a y that's 1, what do I get? A positive or a negative for my second derivative? I get a negative, right? Plug in 1, I get negative 25. Well, second derivatives tell me what? Concavity. On the top of a circle, what are we? Concave down. Oh. Now let's look at the negative y's. Down here, if I plug in like negative 1 for a y, I'll have a point over here. Negative 1 cubed is still negative 1. The negative times the negative would make that a positive. Look, I'm concave up down here. Right? Probably really difficult to see that up here, but once you get all the way down here, you're like, oh yeah, concavity, got it. Sweet. All right, let's try with this. Let's see if you guys can take the second derivative and simplify it so that you use your original equation there to simplify. I see some people being like, nope, didn't get that. Okay, I multiplied after distributing stuff. I plugged in this guy, which is 3x squared over 2y. Multiplied the 6 by the 3 divided by 2, got 9. Multiply your x squared, got x to the 4th over y. Now, I got a fraction, try to subtract from this, give it a common denominator, make it one fraction. Giving me 12xy squared minus 9x to the 4th over y, but then I multiplied by this 4 y squared in the denominator to make it 4y cubed. Okay.
So you take the y under the 9x to the 4th.
Yep. So this became times 1 over 4y squared. So after I found the common denominator, I multiplied by 4y squared. Okay? So now I got 4y cubed. Now I have 12xy squared minus 9x to the 4th. Now you could have done it either way, but I like this y squared is equal to x cubed. So whenever I saw y squared, I replaced it with x cubed. So I have a y squared up here, it becomes x cubed. I have a y squared times a y down here, so turn that into an x cubed times a y.
How do you know how to do that?
You just kind of go with it.
I got you up till there.
Yeah. Well, did you substitute in the x cubed for the y squared?
That's where I lost.
Okay. That's what you're kind of looking for with these second derivatives. You want to use the derivative and you want to use the original equation. So you're looking at developing your original equation in this derivative so that you can use it to help simplify it. So that became x cubed. The bottom became x cubed y. This became x to the 4th minus 9x to the 4th. So 12x to the 4th minus 9x to the 4th. That's 3x to the 4th over 4x cubed times y. You can cancel 3 of those x's, giving you just 3x over 4y. So simple.
Can you go over what you did on the denominator again?
Okay. Y cubed is y squared times y.
Got it. Oh.
So y squared turned into x cubed.
I'm going to need a little.
Now, here's the deal. On an AP test, you are going to be asked to show that your second derivative is equal to this. They will actually give you the answer. So you'll know when you're done or when you're not. If they don't say, hey, show me that the second derivative is equal to this, you leave that first answer and you run. You just get out of there. Okay? You just stop right here. This is your answer. And he said, you never said I had to do anything else. So that's where you stop. Okay? But you need to be prepared to maybe go a little further. I've never seen anything this complex. It's usually find a first derivative and show that it's equal to something a little simpler than this or something like that, but just be prepared. Okay? Okay.
Where does the 9 go?
12x to the 4th minus 9x to the 4th, or 3x to the 4th. Yeah, good question. Okay, moving on. So, moving to different stuff, we are now into intro to related rates. We should be comfortable with these three. Derivatives with respect to x. It's important that you see this x, though, with y, we know is dy dx. The derivative with respect to x of y cubed, we know, is 3y squared, then a dy dx. Like the chain rule. Derivative of the outside times the derivative of the inside. The derivative of y with respect to x is dy dx. Well, the derivative with respect to x can be written as dx over dx. But that's just 1, which is why we say the derivative of x is 1. Well, let's take derivatives with respect to t. It's okay. A lot of times, especially with calculus, we're looking at tangent slopes. The instantaneous rate of change of my y over my x, that's a tangent slope. Well, I can also find the instantaneous rate of change of something with respect to time. Like, how fast is my population growing at this specific moment in time? How much is my particle moving on a horizontal distance with respect to time? Okay? So we can look at rates of change at a specific moment in time. This is taking derivatives with respect to t. So ddting is instantaneous rates of change of things with respect to time. So what's going on at the specific moment in time? Well, what do we think the derivative with respect to t of y is? Good. dy dt. Put it down here. Correct. What about the derivative with respect to t of y cubed? Mr. Kaiser, what do you think?
3y squared, 3y.
Exactly. It's another chain rule deal. The derivative of the outside, leave the inside alone, times the derivative of y with respect to t, dy dt. What about the derivative of x with respect to t? dx dt is correct. Well, what about the derivative of t? 1, exactly. So what you guys didn't know you were doing when I told you here's a velocity equation, t squared plus 2t plus 3, and I told you to find the acceleration equation, you just said, oh, well, it's 2t plus 2. But what you didn't realize is the reason why that's the case is because you were taking the derivative with respect to t, not x. If you did it with respect to x, you would have gotten 2t dt dx, which is like, ugh. So you didn't worry about that. You just left it like this. Okay, so you've already done this, but you haven't done it with these different variables. Well, here are some equations with x's and y's, but I'm taking the derivative with respect to t. Well, it's simply the derivative of the outside, 2, leave the inside alone, times the derivative of the inside, x with respect to t, dx dt, plus the derivative of y squared, derivative of the outside, leave the inside alone, times the derivative of the inside. xy, product rule, just have to use it with respect to t. So f prime, which is not 1, but dx dt, g, plus g prime, which is not dy dx anymore, it's dy dt, times x. Okay, well, find the derivative of this guy. with respect to t. 2y squared minus 3x to the fourth equals z squared. If we can do this, we are on our way to being successful at related rates problems. This is just the beginning. Just wait. It gets so much better. Yep, you're just going to leave it like, well, I mean, maybe, but you get 4y dy dt minus 12x cubed dx dt equals 2z dz dt.
So basically, you define the derivative and then put whatever variable it is on top next to the d.
Yes. Okay. That's the simplest way to explain it, I guess. Yeah. Well, okay, we're not going to do this one, but we're going to get into our beginning types of related rates problems, where I give you an equation and I give you information and I ask you to find something. All right, all this stuff down is all important. Okay. The goal is to find dy dt. We want to see what dy dt equals. We are given y is equal to -2, or when y is equal to -2, and we're given that dx dt is equal to 2. This is all kind of like basic information we are given. Well, to find dy dt, I need a dy dt. To get a dy dt, I'll have to take the derivative of this guy with respect to t. That's the only way I can see what dy dt is, or where it is. I get dx dt plus 3y squared dy dt equals 0. Well, I'm trying to find this, but I'm given information that I can plug in. And I can solve for dy dt. I get -2 divided by 12. That's -2 over 12, or -1/6. Subtract 2, divide by 12. Cool? Okay, let's do another one. This is going to be like the same way that we do these related rates problems, these word problems that we're going to get to next class. You're going to get all your information down, you're going to get your equation down, and then you're just going to take the derivative. Because I need to find dy dt. You won't always have to find dy dt. You'll be asked to find random stuff. Okay. Let's make sure we all have the derivative down correctly. 2x dx dt plus 2y dy dt equals 0. We are told dx dt is 5. We are told y is 3. We are asked to find dy dt. Well, I'm missing an x. I need to find dy dt, but I want a number. I want dy dt equals some number. I don't want the x. Ms. Wise, how can I figure out what that x is? Yes, let's take this y equals 3, plug it into my original equation. I get, and I'm trying to find x here, I get x squared plus 3 squared is equal to 25. X squared will equal 16. X is going to equal plus or minus 4, but we're just going to say it's 4. You'll see why in the future, because we're not going to deal with negative distances.
So just always assume that this is positive for the foreseeable future.
Always assume for the foreseeable future that we're dealing with distances and lengths, and we're not going to deal with a negative length or a negative distance. So we get 4. Then we have all the information we need to find dy dt. 20, 40, 6 equals 0. dy dt equals negative 46, negative 20/3. Okay, that's fun. That's a nice beginning. Here's another one just like it with x, y's, and z's. Don't worry, we'll do those. We will eventually be dealing with equations like these that deal with spheres and volumes of spheres or areas of rectangles. And we will have to take derivatives and find the instantaneous rate of change of these things with respect to time. So I'll show you this on your way out. Please leave your tests on your desk.